MCT4C day 21. The lesson is 3.3 adding vectors. The 3-minute review goal is to solve problems involving vectors. And that was, we had components yesterday, maybe the other day, but was just introduction. And today, what do we see? We see Ferd sitting on a frictionless circular sled on a frozen pond, and two people are pulling on him at various directions, and we want to draw a scale diagram. So let's see if I'm practiced up with my ruler here. The first one is 150 newtons east, so what would be a decent scale? Maybe 1 centimeter is 50 newtons, maybe? And my diagram's not going to be too small. East. And then 200 newtons northeast. Northeast is at exactly a 45-degree angle that way. So let me see if I can. Here we go, 45 degrees. Put a little mark at 45 right there. Put a mark there at 45. All right, there we go, at 45. My protractor out of the way. And, oops, I guess I need my ruler first. This must be a little bit painful to watch me struggle with these things. Let me just see here, up there, dandy, and then that's got to be 4 centimeters long. And we're asked then, after we draw a scale diagram, so this one actually represents, to scale, the 150 Newton force, and this one the 200 Newton force. And this is a 45-degree angle because it's northeast. We have to estimate the direction of Ferd's movement. So notice here that it's the magnitude. The direction we'll think about in a second, but the magnitude isn't going to be 350, is it? Because they're kind of fighting each other here when they're pulling this. One person's pulling this way, the other one's pulling this way. They're not going together. So, I mean, if they're going together in the same direction, say 100 newtons and 200 newtons, and they were actually together, right? They'd sort of be added up like this. This would be 100 newtons, and then, you know, all together 350 newtons, all in one direction, right? I could just add them up, and they'd go on top of each other and help each other. But, oops, they're not, right? They're kind of canceling each other out a little bit, right? So one thing I wanted to mention is wherever I decide that Ferd ends up taking off here, and of course it wouldn't be in this direction because this one's pulling, and it wouldn't be this direction. It's going to be somewhere between, right? But this line, however far I decide to draw it, isn't going to be as long as 200 plus 150. It's not going to be 7 centimeters long. How long I know it's going to be, I don't know. You know, I'm just going to maybe guess. Who knows? We don't know how long that is. Let me put a big red check mark on how long that's going to be, because a red question mark on how long that's going to be. As far as the direction's concerned, this one's stronger, so probably it would make sense that that vector kind of wins out a little bit. If this was 150, they'd go right down the middle, right? It would be, you know, half of 45 would be 22.5 degrees on each side. So you know, if we guess that this one wins a little bit, and then that's might be 20, and this is 25 or something like that, and that's just a plain old guess. It'd be really nice to know, and we're going to find out how to actually work this problem out today. This is going to be one of the questions today, and in fact, one of the topics that we're responsible for is adding two vectors together. So these are vectors, and we kind of know when they're in the same direction, it's pretty easy. They just help each other, and it goes together. We add them like this. But if they're not in the same direction, what do we do? Well, that's today. Adding vectors, like I said, use a variety of tools and strategies to determine the sum of two vectors. And we're actually going to do two techniques. That's why there's two questions that look exactly the same. So we kind of have the same thing as the pond example here. Two forces, and we want to add them up. And remember, it doesn't matter the position of the forces, so we can kind of put them anywhere we want to. So if I wanted to, I could do a copy of the vector u down here somewhere, maybe over here. Okay, and I see it's the same. That vector is the same length and same direction. It's parallel, and then I can move it anywhere I want to. And that's the vector u. And then I want to add v. Well, I could move it into a position where it's similar to what I just saw before, where there's the sled, this big ball on the end, and they're acting on the same position. Remember, a vector, it doesn't matter the position, just the magnitude and size. So if I call that v, then how do I get the result? Well, one person pulls this way, the other one pulls this way. This is the same as the 3-minute review, except for I'm going to tell you the answer. The parallelogram method, we start by doing what we just did. Draw them tail to tail. So that's the tail, and this is the tip here. Tip and tail. And then, parallelogram method, make a parallelogram. I'm going to actually just write in the word make a parallelogram. Okay, what do I mean? Well, this looks like the corner of a parallelogram. I'm just going to sort of copy, if I can figure out how to do this, copy that there, copy that there, and of course you just draw ones that were the same length and size. Now it's a parallelogram, right? This side is the same as this side. That means the vectors are equal. This vector is equal to this side. And in fact, it's kind of like I've got copies of u over here and v over here, and indeed that's what I've done. Now where the resultant is exactly tails to tips. The resultant, and actually that's what the answer to a vector addition is called, is the resultant is tails to tips. So I start at the tails and I go all the way to the tips, like this. I'm going to change the color for that. Make her blue, maybe. Parallelogram method kind of makes sense. And what do you think we're going to make with the triangle method? Yes, it's a triangle. So again, I'm going to copy u down here just so it's out of the way of the... And the idea is, well, instead of a parallelogram, I'm going to draw them not tail to tail, but I'm going to draw them tip to tail, or tail to tip, you could say. So if this is u, that's the one we're starting with, because it's u plus v. And then I'm going to draw v, the exact same vector, tail to the tip of the other one. This is v here. And it's just a copy of the same vector. And then the resultant is a different color, maybe green, eh? This one. Say, well, is that different? It's like exactly the same. Yeah, it is exactly the same. It should be, right? We should get the same answer. For green. So over here, This is the vector u plus v. And this is the vector here, u plus v. Notice that it just order here, kind of an interesting thing. If I went along this side of the parallelogram, this looks like v plus u. If I use a triangle method, v plus u would be the top of the parallelogram. So this shows that it doesn't matter the order that we add these vectors. We're going to get the same thing. And notice this I can do on the smart board. Oops, I don't want you. You stay over there. These vectors are the same. Right? They're the same. Same magnitude, and they're parallel. Oh, triangle. Let me write down the steps to the triangle method. The first step was to, and this is what I did, but let's put it in, get it in your notes, shall we? Draw them tail to tip. So I put the tail of the second vector to the tip of the first, and then I make a triangle. Where the resultant is the third side of the triangle. Is tail to tip. Tail of the first to the tip of the last. And which way you use, we'll see that both of them work fine in either situation, but often it'll be clear whether we're drawing parallelograms or triangles. This shape kind of looks like a bent box. It's got a really fun math name. It's a parallelepiped. 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 That's fun to say. And we've got all the points labeled, and we want to figure out where the resultant is. So here, AB plus BC. I'm going to see if I can do these in different colors so I don't mess up my diagram too much. There's AB, and there's BC. And notice, in this one, we've already got a triangle. This is the triangle method, so the resultant is right here, isn't it? A is on the tail, C is on the tip. A, C. And notice that the order of those are important. Okay. Next one. AB. Maybe I'm going to erase this. You probably can't. I'll just draw over it. Why not? There's AB plus FG. You know, they're not even connected, right? So how can I add them together? They're nowhere near each other. Well, remember, the position of vectors isn't important. So if I wanted to use a vector that's equivalent to FG, but isn't FG, I could do that. So they could be added. And notice, look at that. That's equal to BC. And these are actually the same two questions. I'm going to do a little work down here to show you. AB plus FG, and a vector that I can use to add that's the same. FG and BC are the same vectors, and I get the answer AC again. Same vector. Okay, well, I hope this third one's not the exact same. Otherwise, our diagram's going to be a mess. I'm going to write it down over here, though. CG plus FG. CG plus FG. What colors? Purple. Where's CG? CG is along the top edge like this. There's CG plus FG. Now, is this okay? Can I do this? No. They have to be either tail to tail, like that for the parallelogram method, or tip to tail. So it feels like I'm kind of out of luck here. How can I do this one? Wow. I mean, if I grab this one, well, why don't I put it in this spot where I can go tip to tail? Notice there. There's a vector that's equal to CG, and now I can use the triangle method, right? So here's my answer right there. And letters down here, what did I do? Well, I said instead of CG, CG was equal to BF. And that answer was BG. Notice, and probably some of you that are sharp notice this right away, when we're adding vectors, when the middle two letters are the same, that's good. That's that tip to tail business, right? Tail to tip, and then those sort of are gone, and I'm left with the resultant. And that happened in the first case as well. See that? Tip and tail, the answer is AC, and maybe saw it. Okay, good. Parallelepiped. The boat travels 15 kilometers northwest and then travels 20 kilometers south 80 degrees west. Find the angle the boat turned between legs of the journey. Now, it didn't ask me to, but I'm going to draw a scale diagram here, okay? Just because, you know, I think this is going to be tough if we don't. Whatever it asks here. I'm not sure what it's with. It's asking us to find the angle of the boat. So I'm going to draw a scale diagram. There's where the boat starts. Like that. I'm going to get rid of that one. I don't know what that's doing right there. Okay. Where, and I'm, you know, until you're used to it, you might want to remember north, east, south, and west. And the boat starts by going northwest. So that's off in this direction at an exact 45-degree angle. And it never asked for, excuse me, scale diagram, but we'll be okay. If I can fit my 45-degree angle on here, we'll be okay. Yeah, I think we're all right. 45 is right there. Right? And I'm getting rid of this. And scale, I'm going to say 1 centimeter is 5 kilometers. Then this has to be 3 centimeters long. There. Oopsie, oopsie. There we go. 3 centimeters long this way. Nice. Get an arrow on the end of that thing. That's the first leg of the journey. And then it turns, the boat turns, and goes in this direction. So we kind of got to think of this. There's kind of another set of direction arrows here, right? So I wanted that to be a lot thinner so it wasn't distracting. I'm going to see if I can do that. Let's make it a lot thinner. And then it goes south 80 degrees west. So south would be this way, but then 80 degrees west is up here. But how am I going to do that? I need to measure this angle in here to be 80 degrees. So I'm going to get rid of that. Get my protractor over here. Spin her around. Spin it around. No, not the ruler. Spin her around so that I can measure an 80-degree angle. And notice now it's not fitting on. I wonder if I can write right on my protractor. Don't do this at school. 60, 70, 80. Is there not 90? No, I'm not going to be allowed to do that. What can I do? Oh, I know what I can do. I can try and make this smaller. Yeah, that's better. I'd like to see you try that. No, don't try that. There's 80 degrees about. And then my ruler, I need it to be 4 centimeters. Oops. Oh, really? Four centimeters. Let's get this up here. 4 centimeters long. Oh, and it's just going to fit on the page, isn't that? Well, maybe not, actually. Spin this around. 4 centimeters. I may have to grab this whole thing and move it. Can I do that? Bet you I can. Well, maybe not. Can I get it on there? No, it's not going to fit on. Darn. Ah, that's okay. I'm going to pretend. I'm going to pretend that that's 4 centimeters long. I'm going to put my little arrow on the end. There we weren't asked for a scale diagram in the first place, but the important thing, and I'll mention this when we start getting to the calculations, the important part is that we know about the angles. Okay, and we'll see that. So this is kind of the resultant. The boat went this way, then this way, and now there's the resultant. And I'm going to change the color, and I'm going to put an arrow on the end so I can see where the resultant is. And notice, first leg plus second leg resultant. Triangle method, right? Triangle method. Now if I put some values on here, this was 15, this was 20, and then this is my answer. Right? I'm going to call that the result. In part A here, we did all that work. All it wants us to do is find out that angle that it turned at. Now, as it turns out, that's not very hard at all, because this was a 45-degree angle, right? This was 45 degrees in here, north 45 degrees. So that means Z pattern, this is 45 degrees. We went, after the turn, south 80 degrees west. So that was 80 degrees there. What's that angle? 125. All that work for just that angle, 125. Now, this is what we're really after. Like, how far is this boat from home? The magnitude and direction of the resultant displacement vector. Displacement, remember, is a vector way to say distance. So it's not distance, it was displacement. All right. This feels like the video is getting long. How far along? 22 minutes. Oh boy. Okay, I'm just going to finish this off really, really fast. The magnitude of this is this vector, right? This length. And what is it? Well, the magnitude, it's a triangle, not a right angle triangle, and I got two sides, and I have the inside angle. Well, this is cosine law. Why did we do all that trig, eh? This vector business is all about the trig. And the angle between them is 125. Bada bing, bada boom, calculator action, square root at the end, and you get about 31 kilometers, which makes sense. And had I drawn a scale diagram and not ran off into the page, I could have measured that. Finally, the bearing. Notice the bearing is going to be north so many degrees west, and this was the thing that I wanted to do a scale diagram for, because if this ended up down here, it would have been difficult for us to figure out whether we were south or north, right? But this fairly decent scale diagram, it looks like it's north so many degrees south, and we got to be careful about that. So I'm going to use a different color here. Call this angle theta, because if I find out what this green angle theta is, this was 45, and it's going to be north 45 plus theta degrees west. And when I do that down here, and I'll skip the details because I know this video is long and you guys got better things to do, right? Theta equals 32 degrees, actually. That's what I got the first time. Anyway, you can check that on your calculator. So we'd say the boat has a displacement of 31 kilometers north 45 plus 32, do that in your head, 77, north 77 degrees west. And that's from home, or from start, or whatever. Okay. Should have split that one into two. Sorry, ladies and gents.